Here I'm vodcasting the solutions to the free response section. Okay, standard kinetics problem. We see our charts. They ran 4 experiments. And here we go. They want us to get the order for each of these. So we're just going to go one by one. We're going to do I minus first. We're going to do the chlorite ion or hypochlorite ion and the hydroxide ion. Okay, I'm tempted to start going into some detail about each of these ions, but I'm not going to. Like, this one's basic, and phenolphthalein will change its color and all that stuff. But not going to, because I want to get this done so you guys can have a good night. So, we need to find a place where all the others are held constant. Okay, that's going to happen in 1 and 2. I keep getting emails right here. All right, CLO, so that's going to happen right here. And all the others are constant. CLO, in 1 and 3, it changes and all the others are held constant. And for hydroxide, it looks like that's 1 and 4. Yep, it's 1 and 4. Okay, before I start, heads up, this should be 4.88. I believe I changed that on your paper, though. Okay, so here we go. 1 and 2. 0.2, 0.4, question mark, equals 1.22 and 2.44, question mark is going to end up being 1. 1 and 3, 0.2, 0.4, question mark, equals, again, 1.22 and 2.44, question mark is going to end up being 1. 1 and 4, we are going to get 0.2, 0.4 equals 1.22 over 4.88. Question mark is going to end up being 2. So the rate law, rate is proportional to K, I, which is first order, CLO minus, which is first order, and the hydroxide ion, which is going to affect the rate the most, that's going to be second order. So the overall order is 1 plus 1 plus 2 equals 4. And determine the value of K, including the correct units. So we're going to do value first, and we're going to remind ourselves of the Nick rule to get the units. Let's get the units first. Okay, so for units of K, there's this trick that Nick from block 2 told us today, and I really love it. And you're always going to have 1 over seconds, but you're going to have the molarity symbol in there, and just as a reminder, go through and think about all of the moles per liter as molarities. Molarity per second, right there. All right. So, and it really has to do with the fact that you're always going to be dividing everything by molarity per second. So it's always going to be 1, the order of molarity is always going to be 1 less than the overall order. So in this case, the overall order is 4. So the units are going to be 1 over seconds molarity cubed. So the value, you can pick an experiment, plug it in for K, and we're always going to pick experiment 1, just so we don't have to think. So in experiment 1, the rate is 1.22. So 1.22, I'm plugging everything into the rate law. Is equal to K. I believe that's a 0.2. I believe that's a 0.2. And I believe this is a 0.2 squared. So after you do all that out, K ends up being 762.5. Yep. Seconds -1, meters -3, or 762.51 over seconds molarity cubed. I like this answer, a little fancier. All right, next problem. The catalyzed decomposition of hydrogen peroxide aqueous, that means it's in water, is represented by this reaction. Okay. Assuming the reaction releases heat, so what does that tell us about it? It tells us that the delta H is negative. Draw and label an energy diagram. Use a dotted line to show the effect of the catalyst. It told us that it was catalyzed. Just as a side note, I'll be doing this in class. The catalyst that's used is the iodide ion here, usually in the form of aqueous potassium iodide. Anyways, just a side note. So, very simple. These things are asked a lot, so I know they're really easy, but I tend to try and jam home with you guys things that are asked a lot. Okay? Key features, once again, this is delta H, it's less than 0. That's your energy of activation. Please label EA delta H always. Always label it. Now notice I start and end at the same place. What is the value for the change in delta S? Okay, well, we start with an aqueous thing, which is basically like a liquid. And we go to 2 liquids. We start with 2 aqueous things, 2 liquids plus 1 gas. So it gets messier. Delta S is positive. I hope that's what I have on your key. Yeah. And describe the spontaneity conditions. All right, so in this case, I'm going to go and I'm going to do this part over here. So in this case, delta H is negative and delta S is positive. So this one is going to be always spontaneous. Or you could say spontaneous at all temperatures. Important to remember, temperature is always in Kelvin, degrees Celsius plus 273. Just sneaking that in. Okay. So next part, the kinetics of the decomposition were studied, and analysis for the results show that it is first order. Some experimental data are shown here. All right, so if it's first order, you know, and they just plotted H2O2 versus time, you're going to get something that looks like this. So in order to straighten it out, we would have to take the ln of H2O2. That's all this data is really showing us. So, okay, here we go. During the analysis of the data, the graph below was produced. Okay, label the vertical axis. That's simply going to be the ln of H2O2. Now we can take the slope of that. Okay, write the rate law equation for the decomposition of hydrogen peroxide. Well, we'll do that up here. Rate equals K. There's only one reactant. It's H2O2. And they told us that it's first order. So they're giving us all the information we need. You can put a 1 there. Describe how you would calculate the value of the rate constant K. So remember back, the slope of this line is negative K. So if we took the absolute value of the slope of the ln of H2O2 versus T, that whole thing would be equal to the rate constant K. Is there anything else here? No, nothing else. All right, guys. Have a great day. Thanks a lot.